I only have a few slides for geothermal, but we will spend, as architects, probably the most amount of time dealing with geothermal as an intervention, I guess, or an alternate source of energy for home heating and cooling. It is probably on the bigger picture, just to take a minute and step back, because we're gonna talk for a few minutes about this idea of local geothermal heating system. But there are places in the world where volcanic activity, um, distortions in the tectonic plates or whatever, allow hot magma to get close to the surface and heat soils. So we have these very active regions in the world where we can actually the water can be heated so hot as to directly create steam energy that can then be converted into mechanical energy through a turbine, generate electricity. So here we're absorbing it, and these are cooling towers. You need um, a thermal incline, so to speak, to extract the energy from the turbine. So, but these are relatively small applications for geothermal heating, mostly because they are very unique regions that are not necessarily close to major distribution systems, and they're few and far between, so to speak. More importantly, as architects, we're going to be concentrating on this idea of um, ground source heat pumps and the sources. So at first, I want to just kind of step back and remind us, we've already seen this graphic before. We talk about home heating systems. In this case, the overall goal, and I'm showing a residence, but this could easily be also a commercial building. There's no distinction in ground, geothermal heating for the type of use of the property. But we have this idea of a ground source heat pump. A heat pump is a refrigeration system um, that can transfer heat from one source to another, can pump it up. So we need a source. We could actually take our heat, we can heat a house from air temperatures, but the advantage of using geothermal heat is the heat that is already available in soil. And that's not insignificant. So I don't know if I have the exact quote correct, but if you went down 9 or 10 feet below the soil temperature stays at about 55 degrees year round. And that's a source of heat, and it's a place to disperse heat if we're talking about trying to cool something. So we have many ways to go about kind of extracting that heat. We can dig a vertical collector straight through by digging multiple holes in the field around the house. So an important consideration with all of these is this idea of availability of space. In places where space is less of an issue, um, we might put down these horizontal collectors where we go into a field and dig trenches and place tubing in them. So there's all kinds of variations about these. These would be determined by the geological conditions of the site that we're working with, um, and the cost and the techniques of the installer that they're familiar with, and the availability of being able to disrupt the soil or the surrounding areas. You can imagine in a tight urban situation, you can still have a relatively small site and dig a few wells on a small lot. Out in the country, once again, you might have large pre-existing farm fields where they could be excavated for these types of collectors. And then you may have other sources, like a pond. In this case, the pond could be very useful to to create a cool source of energy for air conditioning during the summer, depending on the climate. Obviously, the downside or the problem with this is the issue of freezing in colder climates. So this idea of geothermal heating, as it directly relates to us, will be around this whole transfer of heat to our internal environment. I say transfer of heat, but it also could be the removal of heat and dumping it out to this system. The reason why these systems are popular is because they have a multiplier effect to the amount of electrical energy that's put into them. So we've talked about this idea of coefficient of performance and their efficiencies. So it has a coefficient of performance of probably 3 or better. So for every watt of electrical energy you put in, you can either you get 3 watts of heat or 3 watts of cooling. And um, that's not a miracle. It's not, it's in keeping with the basic laws of thermodynamics because we're not actually creating or destroying heat. We're actually just moving it. All we're doing is pumping it. So it should be relatively efficient to move heat from one place to another. With that in mind, remember the electrical energy has a cost to it too. And many times when it's compared with things like natural gas, the cost of electrical energy can sometimes be 2 or 3 times the cost of natural gas. And therefore, the efficiencies of these systems are overridden by the cost of the raw material, the electricity or the natural gas that it's being supplied with. And these things vary from time to time. They will vary through your career. So the decisions that we make about the value of these to the environment today will be different than how we consider them tomorrow. Remember about wherever you're locating it, the electrical energy, where it comes from. Is it generated by wind energy? Is it generated by photovoltaic systems? Or does it come from a natural gas power plant down the road a ways? And all of those affect what the ultimate carbon footprint of this kind of use of a renewable resource will be.